All right, for our third and last problem we'll be discussing, we have interstellar intervals. So essentially, for this problem, you're given some string, and these are the constraints. So what happens is you start with like a blank canvas, and for every single cell, you can either paint it white and go to the next cell, or you can paint it some like R followed by B's. So like smallest one you can do is just one R followed by one B. You can also do two R's followed by two B's, and so on and so forth. And however, you're not allowed to go over the end of the array. So for example, if I paint the first cell to be white, and then I want to paint the next three cells red and the next three cells blue, that's not legal because we've ran out of space on our canvas. Okay. And essentially for this problem, for every single cell that's an R in the input, your final canvas has to be an R there. For every cell that's an X, it could be any color you want. And for a B, it also has to be a B. And we need to output the total number of distinct ways we can color this canvas, satisfying all those properties with some modulus, because the answer can be really large. Okay, so first of all, this problem is a very classic, or like right away when you read it, it just feels like, okay, it's probably going to be dynamic programming. And some like signs is like, well, first we have this output the answer mod 10 to the power of 9 plus 7. Whenever this happens, it's almost always DP because you can't like iterate through the number of like combinations. So you kind of have to do some sort of like DP to make it run fast enough. And also we get like a very clear state, right? So the state could just be the index. And this could mean a couple of things. The way we're going to define our state here is the index means how many characters you've already colored in your canvas. So let's go through maybe this example here. Or yeah, so let's say the letters are X, X, R, B, X, X. Then your indices go from 0 all the way up to 6, or up to n in general. And the idea is, if I've considered 0 elements, then my answer is, of course, 1, right? Because there's just one way to have an empty canvas. Okay. And now for every single character, what we're going to do is we're going to think about how many ways are there to transition to here. And we'll actually think about this in terms of like push DP and pull DP, and you'll see why that's useful in a second. Okay, but let's start with the pull DP idea, where we're going to try to compute DP of I, and we are already given all the values of dpj less than I, and we'll just transition from them to build up our answer. Okay, so the first thing is if this cell is an X, then one thing we can always do is just paint this current cell white. And so what that means is we can always transition from dp I minus 1 and add that to our answer. So let's go ahead and mark it as 1. Okay, and then from here, there's not anything else we can do because we can't paint this to be B and this to be R because that like goes out of, like we don't have enough room on our canvas so far to paint like RB. So that's it, right? And if we just analyze this prefix of our answer, it makes sense. So if we have an empty array, the answer is 1. If we have a singular X as our input, our answer is also 1 because the only thing you can do is paint it white. All right. Now for the second X, we still have our transition of let's just paint this white. So we'll go ahead and just add dp I minus 1 to our answer. And now it's a bit more interesting because we can also choose to paint this to be RB. And so we can also transition from index 0. So let's go ahead and change this to 2 now. And if we do a quick sanity check, this checks out because it can either be white, white, or it can be RB for a canvas of just like 2 X's, if that was our input, right? All right, so let's go over to our next cell here. So this cell is a bit more interesting because it's an R. And so the first thing to note is our first transition doesn't work because we're not allowed to paint this white. So we're not going to add dp of I minus 1. And then the second thing to note is the other transition we have is we basically want to pick some like number of R's and B's to paint that ends here. And again, there's no possible transitions because you can't paint this to be blue, red, right? And similarly, you can't paint this to be like blue, blue, red, red. Well, for two reasons. One is you don't have enough space on your canvas, and two, it's guaranteed that this has to be red. So there's no valid transition here. So therefore, the answer just stays at 0. And again, if we do a quick sanity check, this makes sense because if our input was just XXR, then the number of ways to paint this is in fact 0 because we can't paint a red without painting a blue in this problem, right? Okay. For our next cell here, we have a B. And again, first we try to paint this cell to be white, but because it's not an X, that's not a valid transition. The next transition we can do is, well, what if we paint like a B here and a red here? That works. So we can go ahead and transition from this cell, and that gives us an answer of 2. Cool. And then we can also try to transition like 2 blues with 2 reds. And we see that doesn't work because that would violate this cell's constraint. And then finally, quick sanity check here. Our answer is either like white, white, red, blue, or red, blue, red, blue. All right, and those are our 2 ways to color this. Nothing else. Okay. And now finally, we can just basically do the same thing for the last few cells. So we start by painting this white. So we'll just add 2 from this transition. Then we can try to do like BR. That doesn't work because that violates this. However, we can do 2 Bs followed by 2 Rs. So this is a valid transition, and that will be transitioning from here. So we're going to go ahead and mark this as 3. Okay. And then finally, we have this cell. So again, you can paint it white. So that's +3 already from here. And then you can also paint this to be BBRR. So again, +1. You can paint this to be B here, R here, and therefore we get +2. And then the final transition that we can do is you can paint 3 Bs followed by 3 Rs. And so that'd be another +1. And that gives us our answer of 6 here. Okay. And this dp that we described as is currently O of n to the third. And let's analyze this real quick. The reason is we have O of n states. And for each state, we have up to n transitions to try, because we can try painting this white. We can also try to paint the last one blue and a red before that. We can also try 2 blues, 2 reds, so on and so forth, up to like n over 2 blues and n over 2 reds. And then we have a final factor of n, because let's say I pick like 2 blues and 2 reds. I need to check if any conditions are violated, right? So in this case, we can see that, oh, the 2 blues, 2 reds doesn't work because it violates the blue that we need on index 4. And that's where our O of n cubed comes from. Okay, so let's start by getting our runtime down to n squared, which would pass the next 2 test cases. And what we notice is that we can pretty easily trim out the last factor of n. So basically, we want to check if the conditions, like if we can paint some number of blues and reds, and we want to do this check in O of 1. So one easy way to do this is you can just compute a prefix sums of all the Rs and another prefix sums of all the Bs. And then you can just check within the range you're painting, like within the red range, are there any blues? And within the blue range, are there any reds? If there are, then it's an invalid transition. Otherwise, it's valid. Right? So now our algorithm is basically the same, but we still have our n states, and we try all n transitions, and we check which ones work in O of 1. And that's n squared for our 5 and 6 test cases. Okay, and so far we've been talking about this in terms of POL-DP. And let's just quickly analyze, like, how can we speed up our transitions, right? So how do we know which transitions are valid? For POL-DP, let's say we're trying to compute the answer to some dp of I here. And let's just for now assume that it's like an x. Then our first transition is we can transition from dp I minus 1. And this check is simple. It's just, is my current cell x or not? So that one we don't really need to worry about. So let's go over the harder ones to check, which is all the possible like number of blues followed by reds we can do, right? So like, does 1 blue, 1 red work? And then does 2 blues, 2 reds work? And then does 3 blues, 3 reds work? and so on and so forth. And so basically we're checking, like, do we meet the condition for I minus 2? Do we meet some condition for I minus 4? Do we meet some condition for I minus 6? So on and so forth, all the way down to 0. Right. Okay. So now, well, let's break up our condition, which is essentially what our condition is doing is we're going to paint some range blue and we're going to paint some range red. And within the blue section, we need to make sure that there's no reds. And within the red section, we need to make sure there's no blues. It turns out one of these is pretty easy to check, right? So if you consider the range of blues we're painting, we're always going to be painting one more blue for every different transition. So we start with one blue, then we ask, like, for a range of 2 blues, are there any reds? And then for this range of 3 blues, are there any reds? And so on and so forth. And essentially, the first time we find a red, that's going to cap the number of times we can paint blue, right? So let's say there's a red at I minus 3. Then we know the max we can do is we can do 3 blues and no more than 3 blues, because if you do 4 blues, that's definitely going to have a red in it. And 5 blues is also definitely going to have a red in it, and so on and so forth. Okay, so this part of our check is relatively simple. We can just find the first red to our left, and that caps the upper bound of our value of x for our transition. Now, the other one's a bit trickier. So let's suppose there's some, like, blue here at index I minus 2. Well, then your first transition, 1 blue, 1 red is fine. But then when you try to do 2 blues followed by 2 reds, this is not going to work. But then when you do 3 blues, or maybe let me write this, BR is fine, BBRR is not fine. But then starting from 3 blues, this is fine again. Right? So this makes it a bit tricky to figure out which transitions exactly are usable or not. Okay. Cool. So to summarize for now, when we do pull DP, it's really easy to check for our current range, like, of x, or like how many blues and reds we're going to do in a row if it satisfies the blue constraint. But it's hard to check if it satisfies the red constraint of, like, whatever red range I'm painting, make sure there's no blues in it. Right. Let's go ahead and do the same problem with push DP. So let's just quickly go over our sample one more time. So if we're trying to do push DP now, essentially we're going to start from some DPI that's already been computed, and we push to all the transitions we can transition to. So let's go ahead and do this for index for the empty array first. Well, first of all, we can paint the first letter white, so we can transition it here. We can also paint this red followed by blue, so we can transition to here. We cannot do 2 reds followed by 2 blues, because that would violate this one. But we can't do 3 reds followed by 3 blues, so we can also transition to here. Right. Okay. Cool. So that's going to be all the states we transition to. So we just push our DP value to them. So this gets a 1. This gets a 1. Wait, sorry. This gets a 1, I mean. And this gets a 1. All right, next we're here, and we do the same thing. You can paint a white here, so you can just transition this. And then you can also do red, red, blue, blue. So you can also transition to here. And that's it. All right, so this becomes a 2. This becomes a 1. Let's just keep going with this. So from this state, you can't paint the next one white, but you can do a red followed by a blue. So this becomes a 2. You can't do RRBE, so we're done here. This answer is 0, so it doesn't really matter what our transitions are. Here, similarly, we can paint this white. Yeah, we can paint this to be white. We can also paint the next ones to be R and B, so we have 2 transitions here. So we change this to 3, change that to 3. And finally, starting from this cell, the only thing you can do is paint the next cell white. So you add your DP to their DP, and you get 6, just like before, right? So this is the exact same thing, pretty much, except we're just doing push DP. And let's think about the advantages of push DP. So if I'm currently at some index I, and again, let's just assume this is an x, doesn't really matter. Well, one thing is one transition is we go to I plus 1, and this only works if the next element's also an x, right? So again, this is simple, so we won't really worry about it. But let's consider the harder transitions where it's like we're going to put some number of reds followed by some number of blues. So again, maybe we do 1 red followed by 1 blue. Maybe we do 2 reds followed by 2 blues. Maybe we do 3 reds followed by 3 blues. And so on and so forth. And we want to know for each of these transitions, is it valid or not? Okay. Well, let's try to take care of the easy case first again. So let's say I see a blue here at index I plus 3. Okay, so what that tells us is the maximum number of transitions we can do is only 2, because we can do RB, we can do RRBB, but starting from like 3 Rs and 3 Bs, it's going to be invalid. And same thing for 4 Rs and 4 Bs, that's also going to be invalid, because the first blue to the right of us dictates the maximum range we're going to be valid for in terms of what transitions we can push to, right? Okay, now we can actually also think about this in reverse. So what this means is this is going to cap which indices can transition from us. So if we're at index I and we find a blue 3 indices away, let's do a concrete example here. So let's say our current index is like 2, and there's some blue at index 5. Well, what this tells us is we can do 1 R followed by 1 B. So like index. Right. So what this tells us is index 4 we can transition to. We can do 2 Rs followed by 2 Bs. So index 6 we can transition to, but starting at index 8, we can no longer transition to them, and vice versa. If you're at index 4, you can transition from 2. If you're at index 6, you might be able to transition from 2. But starting at index 8 and 10 and so on and so forth, you cannot transition from index 2. Right? Okay. So effectively, what we can do is we can think of this as, so let's go back to thinking about this as just pull DP, but we also considered how push DP works. And so this tells us like for this DP value of I, we can no longer add this answer to some future answer if they exceed, if they're at index 8 or further, right? So what we can do is we can just mark an event to say, okay, at index 8, I need to remember that DP of 2 is invalid now, because from index 8, you're not allowed to transition from index 2 based on this blue cell that we found here, right? Cool. So what we can do is we can just add an event that says at index 8, I'm going to go ahead and change my DP value at index 2 to be 0. All right. And then the second thing is, let's say I'm currying from index 8, right? And let's say there's like a R at 6. So what this tells us is we can do 1 B followed by 1 R. We can do 2 Bs followed by 2 Rs. But we cannot do 3 Bs followed by 3 Rs, and so on and so forth. So this like from our pole transitions, the first R to our left of us is going to dictate like what range we can transition from. And if you have no Rs, then you can transition all the way from the start. And your DP of Is stores all the valid transitions. So if there's a invalid transition due to this B being here, then we would have set the DP at index 2 to be 0. So now what we can do is we can just safely range sum query this. Okay, so let's take a look at example here. So if you're currently at index 8, you can just range sum query from 6 and from 4. Okay. If this R was moved a little bit further, so let's say this R was here, then this means you can go up to like 4 Bs followed by 4 Rs. So that means you can go to 6, you can go to 4, you can go to 2, and you can go to 0. And you're just going to sum up all these elements. And now realize that we're not going to be overcounting our answer, because although like 3 Bs followed by 3 Rs is not a valid transition, this is not a valid transition, that's okay that we're still adding the elements at dp of 2 because we've already processed the event that says dp2 is no longer a valid transition for all future like dp values. So we've actually set it to 0, right? So when we sum this element from here, it's not hurting us. Cool. Yeah, so there's a few ways you can implement this. The first way is you can treat your DP array instead of as just a normal array. Just use a binary index tree. Because if you think about the two operations we need to do, basically we need to be able to set some elements, and we also need to range some query. And binary index tree allows us to do both. And this gives us a O of n log n runtime. Yeah, so essentially just sweep from left to right. At each dp of I, you calculate at which index it'll stop being a valid transition, and you add an event to set it itself to 0, starting from that index. And then the second thing you do is, based on where your first red to your left, that tells you what range you're allowed to range some query from. So again, the example here is if you're at index 8 and the first red's at index 4, you can query anywhere from 0 to 8. Let's say you were at 8 and they're at like 7. Then the only thing you can query from is 6, right? Because you can do BR. So let's say you are a red, then there's nothing you can query because there's no number of Bs you can put, right? Okay, so you can basically take the difference between the first R to your left and your index, double that, and that's the range of valid queries. Now, one other thing is we only want the indices with the same parity as us. So for example, if I'm currently at like index 8, then I only want the sum from 6 and the sum from 4 and the sum from 2 and the sum from 0. I don't want the ones from 1, 3, 5, 7, right? Similarly, if I'm at index 9, I only want it from 7, 5, and 3, and so on and so forth. So what you can do is you can split your DP array into 2 separate bits. One bit can store the odd indices, and one bit can store the even indices, and then you can just query from the correct one. And then one last note is this current runtime is n log n. You can also implement this in O of n with like a 2-pointer idea, and I'll explain how that works. So let's take our example from, let's say the current DP of I is a R, right? Then basically what this means is you're going to be resetting your answer. So whenever you get an R, your answer is automatically 0. And the valid range that you can query is just like nothing, right? You can't query anything. Okay. Now think about what happens when you move 1 to the right of that. Let's assume this is not R. So let's just assume this is X. Well, then essentially your range of valid queries goes from nothing to just 5, right? And then what happens if you move 1 more? So let's say now you're at index 8 and the previous R was at 6. Well, now your range of valid queries extends 1 more. So now it goes from like, it includes this 4. So effectively, as you're moving along, as you're iterating through I, assuming you don't get a new R, then your range of valid queries just goes left by 1 every single iteration, right? And then whenever you do hit another R, you just reset. Your DP value is 0, and your range is reset back down to nothing. Just nothing. Okay, so that's how you can basically do this with like sliding window or 2-pointer, where like every iteration you don't find an R, you increase your window size by 1. And then whenever you do find an R, you reset your window size to 0. And this way, as you're increasing your window size by 1, you can easily just add the new element to the cumulative sum, rather than doing like a range query. So basically, you're still doing that range query, but you're just pre-computing what the range sum would be as you move your window 1 by 1. And then the other thing to note is, let's say you also have to deal with the fact that some DP values expire. So let's suppose what happens is you're currently at index 8, and that means your valid range of queries goes up to 4. But let's say at index 9, your new valid range of queries goes up to 3. But what happens if like one of the DP values expired? So let's say DP value of 5 expires at 9? Well, whenever you get one of these expiration events, you need to check, is that value currently inside your range of like valid transitions? And if so, not only do you have to set this DP value to be 0, you also have to subtract whatever it was. So let's say it was 3, you change it to 0, and you also subtract 3 from your cumulative sum of your like window. Yeah, and so if you do this, you can do this problem in O of n, and you don't need to use a binary index tree. So I think this is probably slightly easier to implement, actually, if you think through it first, and it runs faster. Cool, and that's all the problems for this goal contest.
Thank you, Yibo. Thank you for spending time with us to share the solution. I have a last slide to share with the team. I think all of you might know ACM have achieved pretty good results. And let me share my screen here. USACO contest, ACM, we have more than 300 students achieved the USACO silver and above, more than 60 students in the platinum division, and 27 joined the finalists, while 2 EDOI medalists and 1 RI good medalist. All of them got this, 3 of them got MIT offers. Last year, we have 11 students received MIT offer. Here are the classes we provide. We have on-site camps. It's coming in December 26th, in 2 weeks, and it will 1 week in the South Bay, San Jose. We also have a summer camp. It's 10 days from the end of July. We have a year-round weekend classes. It's 4 quarters a year, 10 weeks per quarter. In addition, we have USACO mock test. This is also important to help you to prepare for the USACO. We have grandmaster classes for the USACO Gold, Platinum Camp, and the IOI. If you are interested in EPCS, you might try our EPCS classes. Okay, great. That's all for today. If you have any questions, you might email us visit our website. Great. Hope you enjoyed the USACO contest. It's a long journey for you to come to the USACO Gold level. Congratulations. Sometimes it's a challenging task. Hope you enjoy that and keep improving your coding skills. If you are lucky to pass USACO Gold, that's a great milestone. If not, I think you should feel very confident and comfortable with your achievement. You're already here. You can pass Google interview without any doubt. The algorithm and the data structure interviews. Okay, great. Thanks, Yibo, again. So hope all of you have a good week and happy holiday. Thank you. Bye.